with means. Sometimes instead of means, we're dealing with proportions. Okay, and we can deal with proportions very much the same way. We can assume that many proportions, or we can, it happens that many proportions can approximate a normal distribution. In fact, there's a term, normal approximation to the binomial distribution, right? Any of these proportions are binomial distributions, right? You have two choices: either you're male or female, either you are immunized or not immunized, either you have diabetes or you don't have diabetes. So you get a proportion, like 3.7% of the population has diabetes, or 80% of the population has been, P is 80%, 80% of the population has been immunized, and so on and so forth. Let's take a look at an example of this and apply the central limit theorem to this proportion, to this binomial. We observed 28 immunized patients in a random sample of 70 patients. We randomly sampled 70 patients out of some large population, say an entire hospital or a village somewhere in, overseas or something like that. So we've randomly sampled that population. We randomly sampled 70 people. 28 of them were immunized. Okay, let's say we're working on polio immunization. It's very big right now, right? They're trying to eradicate polio all over the world. So let's say 28 in this particular part of the country, 28 out of 70 randomly selected patients were immunized. What proportion of the patients were immunized? I'm going to say P, and I'm going to put a cap on it to indicate my sample proportion. Okay, that's equal to 28 over 70. So what percentage is 28 over 70? Well, we can calculate that easy enough. I'm going to do it using this calculator. 28 divided by 70. That's equal to 40%. That was pretty convenient, right? That's equal to 0.4. I'll call it 0.40 for the hell of it. Okay, so now I know the middle of my distribution. I suspect that I'm not really interested in the sample population. I'm interested in the population for the entire the proportion for the entire population. I'll call that P0. The entire population. What is that level of immunization? Well, in my sample distribution, I know P cap, my kind of like X bar, that's equal to 40%, 0.40. Well, I know that I took a decent sized sample, 70 people, and I'm pretty confident that the real population proportion, P0, that's pretty close to my P cap of 0.0. But I'm never going to actually know this. This is not something that I'm capable of knowing unless I go out and check every person in the country, for instance, and see if they're immunized. So I'm not going to know that, right? So I'm guessing at that. Well, I think this is a good approximation of it. But now, again, just like before, I need to describe how accurately, what kind of confidence that I have in that being the actual proportion for the immunization in the population, right? Not just in my sample. So just like before, if I want a confidence interval, 95% confidence interval, I want to know, well, what's 2 standard deviations below and 2 standard deviations above for this proportion, right? Or this time I'm going to get a little bit more precise, 1.96 standard deviations below and 1.96 standard deviations above. What range does that give me? And just like before, I can use a formula, right? My confidence interval is equal to P cap, right? Plus or minus the 1.96 times the standard error, the distribution of all, if I had repeatedly sampled 70 people. Well, what do I need to know my standard error? Before, I needed to know sigma. Well, when we're dealing with a proportion, I don't really need to know sigma anymore to calculate this. I can use a formula that says standard error is equal to P cap actually, times 1 minus P, right, I'll put that in parentheses, over N, and take the square root of the whole thing. That formula is going to give me my standard error. I'm gonna do that right now. So I just get this out of the way so we can get that number. 0.4 times 0.6, 1 minus p is 0.6, over 70. And we want to get the square root of that. So I'll get my calculator out. I'll do the inside of the square root first. So let's see. Let me clear that out, make sure it's clear. 0.4 times 0.6 is equal to 0.24 divided by 70. Gives me a pretty small number, but then I'm going to take square root of it. So, square root is the number which when multiplied by itself gives you the original number. So it's, the square root of that is going to be a bigger number. It's 0.058. 0.058. I'm going to take a liberty here just to make our math a little simpler. You should probably, if you rounded this, at the worst you'd want to do is 0.059 maybe, right? Because that 5 will round up. But maybe even if you can avoid it, just keep working in Excel or in your calculator and don't round until you necessarily have to. But for our purposes, I'm going to call this 0.05. I'm going to call it 0.059. Okay, I'll be a little bit accurate. Okay, this is equal to 0.059, or a little less than 6%. Okay, that's my standard error. So now my standard error in this formula has to be multiplied by 1.96. So let's see, 1.96 times 0.059. See, I increased my error automatically because I didn't round it. Now I'm going to double the error by doing this, but that's okay. You know what? If it's still there, oh, it's still there. So I can just, I'm not even going to increase my error. I'm going to multiply by, where's multiply? Times 1.96. And that's equal to 11.5, 0.115, I'm going to call it. 0.115. Okay, or 11.5%. You can look at it that way too. Okay, so that is this portion of my calculation, 1.96 times my standard error. Okay, and that's 1 and 115 and so on and so forth. Okay, so now I'm going to say, let's see, I'm going to say my p-value is 0.40, right? So 0.40 minus 0.115 is going to be equal to, let's see, 40 minus 11 would be 39, and it's going to be a bit more, so 38.5, 285. Okay, everybody agree with me there? That if I subtract 0.40, if I subtract 0.115 from 0.40, it's going to come out to be 0.285. If I had subtracted just 11% from 40%, it would have been 29%, but this, I'm subtracting a little bit more. Okay, and if I add it, plus 0.115, that's going to be 0.515, right? So my confidence interval is a proportion of 0.285 to a proportion of 0.515. So somewhere between, I'm 95% confident that somewhere between 28 and 52% of this population has been immunized, right? And that's my 95% confidence interval. If I was looking for a 99% confidence interval, instead of using 1.96, I would have used 2.58. Instead of using, if I'm looking for a 90% confidence interval, I don't need to be that confident, so I can make a narrower range, I would use 1.64 instead of 1.96. That's the only difference, okay, in calculating those other confidence intervals. Now, notice I didn't know the population standard deviation here, and yet I did this problem anyway. One of the rules about doing confidence intervals for proportions is your sample size has to be at least 30. Right? You have to have a sample size of at least 30. Not only that, but both sides, remember here, now we got 28 people that were immunized out of 70. That means we had 42 people. Am I right? 42, 42 people that were not immunized, right, out of 70. 28 that were, 42 that weren't, that adds up to 70. So 28 out of 70 were immunized. Both of those sides have to be greater than 15. right? By setting a limit on the minimum sample size, not only for overall, but also for each side, right? We get into a position where we have a better estimate of the population distribution than if we took a small sample. So by avoiding a small sample, we are making it so that we can go ahead and calculate our confidence interval without worrying about not knowing the real standard deviation for this population. Okay. And in fact, remember that sample that I did before where the sample was where the sample size was equal to 100? When we take even a regular mean, when the sample size is very large, we're going to be able to make certain kinds of assumptions about that also. But let's just stick with this where we are right now, and we're going to go on to the next